Hi guys, come back to Physics 150. The next part will be our electric flux. Okay, electric flux. So electric flux is related to electric field. So we define electric flux by formula first. Okay, so that is our 1.5 just now. So 1.5 is electric flux. Okay, electric flux has a symbol of phi. Okay, have a symbol of phi. So this one you pronounce as phi. Okay, phi. The small letter of phi is this. Okay, this one is big capital letter for phi. Is Latin. Okay. Next one is what is electric flux? Okay, so electric flux phi is defined to be the dot product of electric field and the area of a surface. Okay, so it's simply a mathematical product that actually help us to calculate the effect of electric field on something else. Okay, so our formula will be this: phi is equal to the dot product. Dot product, what is dot product? You already learned dot product. Okay, so the dot product of electric field is this one. So our dot product is E dot A. Okay, now you might be very curious. What is this? This one is a surface area vector. Now you are even more curious. Since when surface area is a vector quantity? Well, it is a vector quantity. Well, just that in Form 4, Form 5, because you are still a bit less intelligent. I don't want to call stupid. Okay, it's actually the same. Okay, so is what we call that is at that level you don't need to deal with area as a vector, but now you're in diploma. For diploma matrix and also the Form 6, this A level, they need to treat vector the surface area sometimes as vector, sometimes as a scalar. So this type of vector, which is not all the time a vector, is called a pseudo vector. Okay, so A is a pseudo vector. So what is pseudo vector? I give you the symbol, not symbol. So area is a pseudo vector, not sumo. Pseudo vector. Vector is of course a vector, something that has magnitude and direction, and then pseudo is something that is not entirely real. It's something in BM we call palsu, olok. Okay, so that is pseudo vector. But we don't want to care about whether they're pseudo vector or what, but you have to deal it as a vector from now on. So now what is dot product? Dot product means you end up like this. Dot product means E times A times cosine theta. Your theta is the angle between the vector E and A. Alright? So that is our electric flux. So now, what is the unit for our electric flux now? From this formula, the unit of our electric flux is the unit for the electric field, which is Newton per Coulomb, multiplied by the area meter square. Cosine theta is just a ratio, no unit. So we have end up like this: Newton meter square per Coulomb. Or you can also use this unit, because as we know, electric field has two units, and one is Newton per Coulomb, and another one is volt per meter. Okay, and then you end up with voltmeter. Okay, voltmeter. So that is two of the units that you can use for our electric flux. Okay, so now we want to look at in more detail physically. Okay, from geometry point of view, how do we draw this? Now let's assume you have a surface area. Okay, you have a surface area like this. Surface area with a surface A. Okay, the size is A. Let's say if this is A, this is B, so your area A is equal to A times B. All right. Now you have, from this our point of view here, this is the surface that is pointing at us. The other side is another surface, so something like this. I want to find something rectangle here. Okay, never mind, use this one. So when I put like this, okay, you see like this. This is a surface that is, you can see, and then behind there got another surface. We are looking at the one in the front. Okay, so the surface in the front is going to have a surface area vector pointing out directly at 90 degrees. This is the area vector for this surface. The other surface has a vector point in the opposite direction compared to this one. Okay, so now we're going to put this surface area in our electric field. So I'm going to use electric field, green color. Okay, our electric field. So when you put in an electric field, some electric field will simply passing through the edge without touching the surface area. Some will pass through, okay, like this, and coming out here. And then some will pass through this location, okay, and out here, same thing. Some will pass through this point, which is very important to us now. So this is the electric field E. Okay? They are all the same, they are all electric field E. Now, there is an angle, if you look carefully. This angle here is the angle theta. Angle theta is an angle between A, vector A, and vector E. And then if we draw a line through that surface area, then we can see that it's more like three-dimensional now. This one is 90 degrees from the surface. This line is actually called the normal line. You already learned that one in Form 4 in your optics about reflection and refraction. The angle you use in the Snell law is referred to the line of normal. Okay, so this one you can treat it something like a normal. Except normal line, we don't have direction. We only as a guideline, 90 degrees from the surface. But this one is not only a normal line, but it has a direction away from the surface. That's why it's called an area vector. Okay, so I can write there, area vector. Okay, area vector. So E is making an angle theta, but E also making another angle here. This angle I will call alpha. But alpha is not the angle we use for our calculation here. Our formula here is going to use theta. So the theta is between the A and the E vectors. This angle alpha is called the glancing angle. We don't use glancing angle in our normal calculation, but we use glancing angle somehow in X-ray. You're going to learn X-ray in part 5, I believe. Part 4 or part 5? Part 5. Physics 310. Sorry, part 4. Physics 310. Modern physics. Okay. So that is our diagram showing exactly what happened here. Okay. So that means be careful. Question like this, normally you have to visualize something like a three-dimensional. Okay. So we start with example here. Okay. Our example 1. Okay. Our example 1. So example 1, I'm going to have a diagram. So instead of rectangle, I give you a circular shape. Okay, a circular shape, something like this. Okay, circular, but because it is at a certain angle, so you don't see it is totally round. So you have a circle like this, and this is the center of the circle. And the area is pointing here. This is an A, and there is an electric field passing through, and the electric field is here. That is the E. Okay, and let's assume your E is like 2.50 10 to the power 5 Newton per Coulomb. See, pointing to that direction, but it doesn't matter. Okay, and then you have this guideline. So you are given this alpha is equal to 40 degree. Okay, alpha 40 degree. Now the question is like this. A circular, okay, surface has radius of 70 centimeter. Okay, 70 centimeter, and placed in an electric field of 2.50 10 to the power 5 Newton per Coulomb. Alright, calculate the electric flux through the circle. Okay, through the circle. Alright, so electric flux, use this formula. So our solution is here. First, you have a circular surface of radius 70 cm. Okay, so that means you need a formula to calculate the circular surface area, which is pi r square. Okay, pi r square, right? So, but this one is 70 centimeter. You have to change to meter later on. So first we write down the formula. It is EA cosine theta. So we put in the value E first. E and A is pi r square, and then cosine theta. And then our phi here is E, which is 2.5 10 to the power 5. Okay, and then our area is pi times this one. Radius is 70 cm, 0.7 square. Okay, and then multiply by cosine theta. Theta is here. This is our theta, but alpha is 40, so theta is 90 degree. Theta plus alpha must be 90 degrees, so this one will be 50. Okay, 50 degree. All right. So our answer from our calculator will be this: 2.5 10 to the power 5 times pi times 0.7 square, and then times cosine 50. Okay, so we got this 2.47 10 to the power 5. Unit will be this: Newton meter square per Coulomb. Okay, Newton meter square per Coulomb. Alright. Okay, so now this is a simple example, except the geometry I changed a little bit. It become a circle. Now this is page 1. Next one, example 2. Okay, example 2. So our example 2, now I will say that a circular coil has 200 tons. Okay, and it is placed in a uniform electric field. Okay, it is placed in a uniform electric field of 350 kilonewton per Coulomb. Okay, if the circular coil is rotating, okay, rotating in the field, find the maximum and minimum flux through the coil. Okay, so that is what happened here. You have a circular coil, okay, but that circular coil have 200 tons. Okay, And oh sorry, forgot to give you the radius. Okay, radius here, circular coil at 200 turns, and radius equal to now 45 centimeter. Okay, jot this one down, 45 centimeter. Okay, so it's rotating. So rotating, that means there are so many angles. Okay, so many angles from 0 until 360 degree. But the question gives us some clue. Maximum and minimum. Okay, maximum and minimum. So to know whether it's maximum or minimum is actually very easy. We don't have to worry about how we draw that situation. But what is important is you must know that the cosine function has a maximum of 1 at 0 degree, and then minimum of 0 at 90 degree. So that is the clue that we have. Okay, so you have to know this. So that means the language of physics is mathematics. If you screw up in your mathematics, normally at the same time, hallelujah, you're going to screw up your physics as well. Okay, so that's why we are here to help you to solve that type of scenario. Okay, first we draw our for minimum, our solution is here. For maximum first, okay, for maximum flux, okay, for maximum flux means our electric, the electric field is going to pass through the surface at 90 degree, okay, at 90 degree. So this is our surface area vector A, okay, and then our electric field also pass through like that. Okay, electric field vector. So our theta between them is 0 degree. Okay, but don't forget this one here, you have so many. Okay, you have so many turns here. Okay, you have so many turns. So I draw a multiple one so that you can see the difference between them. So there is a multiple coil. Okay, multiple coil. So it is 200 turns. Okay, 200 turns. But the radius are the same, 45 centimeter. So how do we solve this problem? So maximum flux is equal to EA when your cosine is 0 degree. Okay, so that means both of it is 90 degree from the surface, cutting through at 90 degree. Now 0 degree here, okay, theta is 0 degree because the theta is between A and E. So that is maximum. So we calculate this one first. Our E is given 350 kilonewton. So 0, 0, 0. Okay, and then multiply by pi r square times 0.45 square. Okay, we see what we have here. So this value 350,000 times pi times 0.45 square. Okay, we got this value here, 2.2310 to the power 5 Newton per Newton meter. Is it Newton meter? What's the unit again? Forgotten already. Newton meter square, okay, per coulomb. Newton meter square per coulomb. Is our unit here correct? Okay. Now that is our value for 1 turns. This one for 1 turns. Now for the 200 turns, we call that one the flux linkage. Okay, the flux linkage is the total. That means it's equal to N flux maximum. So that will be 200 times your flux maximum. So we times our answer with 200. So we get 4.45 10 to the power 7 Newton meter square per coulomb. So that is our first answer for maximum. Well, for minimum is very easy. For minimum flux, your minimum flux is, okay, is when cosine theta is equal to 0 when theta is equal to 90 degrees. So if it is 0, we don't have to calculate anything. The minimum is 0. So the flux linkage total minimum is also 0. Okay, so 0 minimum is always 0, and the maximum you only need to do this calculation. But remember to multiply 200 after you calculate that one. Sometimes lecturer like to put the n inside here, but I prefer to do it the other way around, because if you look at the formula carefully, by definition there is no n here. So we calculate that flux, and after that we calculate the flux linkage. All right, so this is the example for the electric flux. Okay, so we finish for this one. So the next one will be Gauss law. Okay, so Gauss law is horrible, is one of the most difficult in physics 150. Okay.